If you physically glue the edges of simple shapes together, like joining a few empty circles at a single point or pasting a solid disk over a gap, you are directly writing algebraic equations. Every spatial connection you make generates a specific mathematical group structure. Consider a wedge of circles from section 71. Circles sprout from a single base point. Each loop adds one independent algebraic generator. Traveling around loop 1, then backwards around loop 2, concatenates into the word F1, F2, -1, forming a free group. We can see this formalized in the text. This is figure 71.1, which illustrates the rigorous diagram of these path-connected spaces intersecting to form the wedge. The rule here is clear. Joining one-dimensional boundaries strictly creates a free group of independent generators. These isolated loops form the raw alphabet of our algebraic structure. Now, what happens if we fill an empty loop by attaching a solid 2D disk, or 2-cell? Section 72 outlines adjoining a 2-cell. We simply take the boundary of our solid disk and glue it directly onto the wedge's loops. Before, a path around an empty circle was trapped, but now, bordering a solid surface, the loop can continuously slide and shrink across the disk's interior, pulling tighter until it completely disappears into the base point. Theorem 72.1 translates this topological shrinking back into algebra. Because the loop shrinks to nothing, the algebraic word representing that specific loop becomes topologically trivial. In our group equations, it now simply equals the identity element, written as E or 1. This is figure 72.1, showing the deformation retract across the attached disk. This visualizes a concept the text calls quotienting by the least normal subgroup. That jargon simply means we take our free group and force the boundary loop's equation to equal 1. Let's test this concept. Imagine a wedge of two circles, called A and B. If we attach a square-shaped 2-cell whose boundary traces the path A, then B, then backwards along A, then backwards along B, giving us the word AB, A inverse, B inverse, what algebraic relation does that new surface create? By adjoining the 2-cell along that specific path, the boundary word equals the identity element. Our path sets AB, A inverse, B inverse equal to 1. This gives us an immediate algebraic consequence. Setting this equal to 1 is mathematically identical to stating that AB equals BA. Here, in figure 73.1, we see the resulting shape. Gluing the edges of a flat square in this exact configuration creates a torus, which is the surface of a donut. Our original free group on two generators has now been quotiented. Because our new relation states that A and B commute, that AB equals BA, the torus yields the free abelian group on two generators, written as Z cross C. The spatial construction perfectly mirrors the algebra. One-dimensional boundaries, like our wedge of circles, add independent generators. Two-dimensional surfaces, like adjoining 2-cells, add relations that quotient those generators. If you found this breakdown helpful, be sure to like and subscribe. We'll keep translating standard math texts into clear, visual intuition in the next video.